is where it gets interesting. If the whole department or process basically gets shut down, all the worker or threads stop as well. But if just one worker messes up, the rest can still keep working. One of the most common places you will see process and thread in action is on web server. So web server like Apache or Nginx handle thousands or sometimes millions of user requests at the same time. However, thread pools aren't a magic solution. They need to be carefully managed. So if your thread pool is too small, tasks will have to wait for available threads, leading to delay. Imagine that there are two threads, thread 1 and thread 2. Now thread 1 has logged resource 1 and thread 2 has logged resource 2. Hey everyone, welcome to Prep Train. If you are new here, I am Sahil Kumar and this is the channel where we break down complex backend engineering concepts into easy to understand bite-sized lessons that will help you level up your skills, whether you are a college student, a complete beginner, or even someone looking to refresh their knowledge. At Prep Train, we believe that learning should not only be educational but also practical, and that is why we are focusing on giving you the tools, tips, and real-world application that can help you land your next internship, job, or even tackle that tricky coding project. Today, we have got a really exciting topic lined up for you. It's something every backend engineer needs to understand: process and thread. Now, you might be thinking, what is the big deal about process and thread? Well, they are the backbone of multitasking in backend system. From web servers handling thousands of requests to your favorite game, process, graphics, and audio simultaneously. Process and threads are quietly doing all of these heavy lifting. Before we dive in, make sure that you hit the subscribe button and turn on notifications so that you don't miss out any of our upcoming videos. We have got a lot of more valuable content coming all your way. Also, don't forget to join our 15 Telegram community. It's a great place to stay updated on latest jobs and internship opportunities, as well as to connect with others who are passionate about learning and growing in tech field. Alright, let me just bring my deck and then we will continue diving deeper into the world of process and threads. Alright, let's start with some basic in the world of backend engineering. Process and threads are basically the fundamental concept that help your system manage multiple tasks at the same time. So what exactly is a process? A process is an independent unit of execution. Think of it like a separate workspace or department in a company. Each process has its own set of resources such as memory, files, or CPU time. This isolation is crucial because it prevents one process from interfering with another. If one process crashes, it won't necessarily affect the others, and that is why we say processes are independent. Now let's talk about threads. Threads are a smaller unit of execution within a process. So imagine them as the worker inside a department. Unlike process, threads share resources like memory or files within the same process. So this makes them more efficient for certain tasks because they don't need to set up everything from scratch and they can work on different tasks simultaneously, but within the same environment. So how does your system manage this process and thread? And that is where your operating system or OS comes in. The OS is like the manager of entire system. It decides which process or thread gets to run at any given time, ensuring that your system can handle multiple tasks without crashing. In summary, process are independent units, while thread are smaller units that share resources within a process. Both are crucial for multitasking, and your operating system basically makes sure that everything's run smoothly. Now, let's make this a little more relatable by using an example. Imagine your computer is an office building. So each process is like a department within that building, working on its own tasks with its own resources. For example, the marketing team might be working on a new campaign, while the finance team is handling the budget. So each department or process has its own responsibility and resources. They don't interfere with each other. But what about threads? Well, threads are like the individual workers within each department. These workers share common resources like office supply, meeting rooms, but they each other have their own tasks to complete. So inside the marketing department, one worker might be writing copy while another might be designing graphics. They are both working towards the same goal and sharing resources, but they are handling different part of the project. Here is where it gets interesting. If the whole department or process basically gets shut down, all the worker or threads stop as well. But if just one worker messes up, the rest can still keep working. This is why threads are faster and more efficient for certain tasks, but they also depend on the process that they belong to. This example helps us to understand and highlight two key points. Processes operate in isolation while threads share resources within the same process. Both are crucial for handling different type of tasks in a system and both have their own advantages and challenges. Now that we have covered this example, let's take a look at the key difference between process and thread that will help us understand their specific role even better. Let's now dive into the key difference between process and threads, which will give you a clear picture of how they function in a system. The first major difference is that processes are isolated. This means that each process has its own memory, resources, and environment. Think of them like departments that don't share any material or information with other department. This isolation helps maintain stability because if one process crashes, it won't affect the others. However, this also makes processes heavier. They require more resources to set up and run because they need their own memory and environment. On the other hand, threads are much lighter. They share memory and resources within a process, making them faster and more efficient for certain tasks. However, this also means that threads are more closely linked to each other. So if one thread goes down, it can affect the other thread within the same process. This is why threads are described as shared unit while processes are independent. Another key difference is how they communicate. So inter-process communication or IPC is required when processes need to talk to each other. This can be complex and slower because processes are isolated. Threads, however, can communicate much more easily since they share the same memory space. In summary, processes are isolated, heavier, and communicate through IPC, while threads are shared, lighter, and can communicate more easily within the same process. Both have their own strength and weakness, and choosing when to use each depends on the specific need for the system. Now that we have explored processes and threads, let's dive into how your operating system or OS actually manages multitasking. This is where things get really interesting because multitasking is what allows your computer to run multiple applications at the same time without crashing. Now, there are two main types of multitasking that operating system use: preemptive and cooperative multitasking. So in preemptive multitasking, the operating system is in full control. So it decides when a process or thread could pause, or basically when it should pause and then when another should take over. Think of it like a manager at a company who is constantly checking in on different departments, making sure that each get a fair amount of time and resources. When the manager sees that one department has enough time, they switch focus to another department. This ensures that no single process or application hogs all the resources. On the other hand, cooperative multitasking is a bit different. In this setup, process or thread must voluntarily give the control. It's like one department in a company deciding, okay, we have done enough work for now, it's time to let another department take over. While this can work in certain scenarios, it's less efficient because if one process does not give up the control, it can hog all the system resources, causing everything else to slow down or freeze. Most modern operating systems like Windows, Mac OS, or Linux basically use preemptive multitasking because it provides more control and ensures that all process and thread get their fair share of resources. But here is the catch: switching between processes and threads, known as context switching, takes time and resources too. So each time the OS switches from one process or thread to another, it has to save the current state or the process and then load the state of the next one. This can lead to performance slowdown if there are too much of context switching happening. This is why having too many ops open in your computer feels, slow. In summary, the OS manages multitasking by either preemptively controlling when process and thread switch or allowing them to cooperate. However, context switching comes with its own overhead, which is why efficient management is crucial. Next, let's take a look at some real-world example of how process and threads are used in everyday applications. Now that we have covered how OS handles multitasking, let's look at some real-world example of how process and threads are used in applications that you interact with every day. One of the most common places you will see process and thread in action is on web server. So web server like Apache or Nginx handle thousands or sometimes millions of user requests at the same time. When you visit a website, the server creates a new thread to handle your request. This allows the server to manage multiple users simultaneously without crashing. Each thread processes a user request, fetches the necessary data, and then sends it back. Without threads, the server would need to handle one request at a time, which would be incredibly slow and inefficient. Another great example is video games. Take a game like PUBG. For instance, multiple threads are running in the background to handle different tasks at the same time. One thread might be responsible for rendering the graphics, another for calculating physics, yet another for managing the game sound effect. This allows the game to run smoothly with all these elements happening simultaneously without causing delay or crashes. Of course, this also applies to everyday multitasking on your computer. Let's say you have Spotify, Chrome, and Slack open at the same time. Each of these applications run on a separate process, and within each process there are multiple threads. So one thread in Chrome might be loading a web page, another might be playing a video in the background, and yet another might be managing notification. This is how your system can handle multiple apps all at once, all without slowing down, so as long as resources are managed efficiently. So whether it's a web server or a video game or your everyday apps, process and threads are essential for keeping things running smoothly. They allow systems to multitask efficiently, providing users with a more seamless experience. Now that we have seen this real world example, let's discuss two more things: concurrency and parallelism. Now that we have covered process and threads, let's talk about these two concepts that are often confused with each other but are essential for understanding how multitasking works. So in backend system, concurrency and parallelism are very important topic. First, let's define concurrency. So concurrency involves basically multiple tasks making progress at the same time but not necessarily running simultaneously. Think of it like having two projects on your desk and constantly switching between them, working a little bit on one then switching to the other. In this case, you are making progress on both, but they are not happening at the exact same moment. This is how many systems handle multitasking, whether tasks are switched in and out of focus, allowing them all to progress without any one task dominating the system resources. Now let's move on to parallelism. So parallelism is when tasks are actually happening at the same time. This is possible when you have multiple core in your CPU. So imagine two people working on different tasks at the same time. So one person is typing a report while another one is analyzing the data. Both tasks are happening simultaneously and there is no need to switch between them. This is true parallelism, where multiple tasks are running at the exact same time. The key difference between concurrency and parallelism is that the concurrency is about task switching, multiple tasks making progress in an overlapping time period, but not necessarily running at the same time. On the other hand, parallelism is all about simultaneous execution, multiple tasks actually running at the same time on different cores. Both concurrency and parallelism are crucial for efficient multitasking in backend system. Concurrency allows system to handle many tasks at once by switching between them, which can be done at a single core. Parallelism, on the other hand, allows tasks to run simultaneously, which require multiple cores. In modern system, you will often see both concurrency and parallelism working together. For example, a web server might handle multiple user requests concurrently by switching between them, while some tasks like image processing might be handled in parallel on multiple cores. Understanding this concept is key to optimizing the performance of backend system, especially when you are dealing with high traffic or resource intensive application. Next, let's explore thread pools, a crucial mechanism for managing thread efficiently in a system. Now that we have covered concurrency and parallelism, let's talk about a practical tool that helps manage thread efficiently in backend system, which is thread pools. A thread pool is essentially a collection of reusable threads that are available for performing tasks. Instead of creating a new thread every time a task needs to be executed, the system pulls an existing thread from the pool and assigns it to the task. And once the task is complete, the thread is returned to the pool. This allows the system to avoid any overhead of constantly creating and destroying threads, which can be expensive in terms of resources. Think of a thread pool like a team of workers waiting for tasks to arrive. When a new task come in, the manager assigns it to one of the available workers. Once the worker finishes the task, they return to the pool ready for the next task. This is similar to how thread pools work. They allow the system to efficiently manage multiple tasks without the cost of creating new thread each time. Why is this important? Well, creating and destroying thread can be a time consuming operation, especially if you are dealing with a large number of tasks. By reusing thread, you avoid this overhead, which leads to a better performance, especially in systems that handle high volume of tasks like web server or database server. Thread pools are particularly useful when you have many small short-lived tasks that needs to be processed in parallel or concurrently. For example, a web server might use a thread pool to handle incoming requests, and each request is assigned to a thread from the pool. Once the request is completed, the thread is returned to the pool, ready to handle another request. This allows the server to handle hundreds or even thousands of requests efficiently without running out of resources. However, thread pools aren't a magic solution. They need to be carefully managed. So if your thread pool is too small, tasks will have to wait for available threads, leading to delay. And if it is too large, you might end up using too much memory and CPU, reducing the overall performance of your system. So in summary, thread pools are a great way to manage multiple tasks efficiently by reusing thread, and they help reduce the overhead association of creating and destroying threads, and particularly useful in system that can handle many small tasks. Next, let's move on to a potential issue which you can run into with threads: deadlock. Now that we have discussed how thread pools can help manage tasks efficiently, let's talk about a potential problem that can occur when threads don't cooperate: deadlock. So deadlock happens when two or more threads are stuck waiting for each other to release a resource and neither can move forward. It's like two people trying to go through a narrow door at the same time, but neither one is willing to step aside. So they both get stuck. So in the context of process and thread, deadlock occur when two or more threads are holding onto resources and the other thread needs to complete their task. Here is a simple example. Imagine that there are two threads, thread 1 and thread 2. Now, thread 1 has logged resource 1 and thread 2 has logged resource 2. Now, thread 1 is waiting for resource 2 to be released by thread 2, and similarly, thread 2 is waiting for resource 1 to be released by thread 1. Now the thing is, since both threads are waiting for each other to release the resources, neither can move forward and the systems become stuck in a deadlock. Deadlocks are particularly dangerous because they can cause entire system to freeze or crash. So if you are dealing with a system that handles critical tasks like web server processing requests or a database managing transactions, a deadlock can bring everything to a halt. This can lead to delays, lost data, or even complete system failure. So how can we avoid deadlocks? One common strategy is to ensure that threads always request resource in a specific order. For example, if all threads are required to request resource 1 before resource 2, then deadlock are less likely to occur because one thread will always be able to obtain the resources it needs. Another strategy is to use timeouts. So if a thread can't obtain a resource within a certain time frame, it will release any resource it's holding and try again later. This prevents thread from being stuck indefinitely and reducing the likelihood of a deadlock. Deadlock are a challenging problem, but with proper resource management and attention to how threads interact, they can be avoided. Alright, let's quickly wrap everything that we have covered in today's video with a quick recap of key points. First, we talked about processes. These are independent units of execution, meaning they have their own memory and resources because they are isolated from each other. Process needs inter-process communication or IPC to communicate with one another. This isolation helps maintain system stability, but it also makes process heavier and slower to switch between. Then we moved on to threads. Threads live inside a process and share resources like memory and files, making them much lighter and faster compared to processes. However, because threads share resources, they are more interconnected, meaning if one thread crashes, it can affect the entire process. Threads are essential for multitasking within a single process. Next, we explored how the operating system or OS manages multitasking. There are two main types: preemptive multitasking, where the OS controls when a process or thread switch, and cooperative multitasking, where processes voluntarily give up the control. So the OS use context switching to switch between the tasks, but this can add some overhead, which is why having too many tasks open can slow down your system. We also talked about concurrency versus parallelism. Concurrency is when your multiple tasks make progress by switching between them, while parallelism is when tasks are actually running simultaneously on different cores. Both are essential for efficiently multitasking in backend system. After that, we discussed thread pools, which are collection of reusable worker threads, and thread pools allow system to handle multiple small tasks efficiently without the overhead of constantly creating and destroying thread. This is particularly useful in high traffic system like web server. We also covered deadlock, which happens when two or more threads are stuck waiting for each other to release resource. This can freeze or crash a system, but with careful resource management, deadlocks can be avoided. Finally, we looked at some real-world example of how process and threads are used in everyday application. We saw how web server like Apache use threads to handle multiple user requests, how video games like PUBG uses threads to manage graphics, physics, and sound, and how multitasking apps on your computer uses process and threads to run smoothly. So in summary, process and threads are the backbone of multitasking in backend system, whether it's keeping your apps running smoothly, managing multiple users on a server, or ensuring that your game does not crash. Understanding this concept is a key to becoming a skilled backend engineer. Thank you so much for sticking with me till the end of this video. Today we covered the essential of process and thread and how they work, why are they important, and how they are used in real world application like web server and video games. If you found this video helpful, don't forget to give it a thumbs up. Your support really helps this channel to grow and motivate us to keep creating more content just for you. Also, if you haven't already, hit the subscribe button and turn on notification to stay updated with all of our latest videos. We have got some really exciting topics on backend engineering coming up, so make sure that you don't miss out. Also, if you're looking for even more opportunities to learn and grow, join our Pipton Telegram community where we post the latest job and internship update. It's a great place to stay connected and stay informed. Thanks again for watching, and I will see you in some other video where we will dive into some key concepts from backend engineering.